Let's begin. We don't have much time, so I'd like to use every minute to prep for the exam. So I was going back and forth whether we should do the Q&A session today versus next Tuesday, just before the exam. Then we concluded that it's best to do it today. It gives you some time over the weekend. Hopefully you're studying over the weekend for the exam. Those materials will be available to you. And then next week, Ariana and Ainsley will be running the help sessions essentially as additional Q&A to help you prep for the exam. Okay, so without further ado, let's get started. These are the questions lifted anonymously out of the feedback that you provided. Thank you for doing that. Super helpful. And I think this is one of the best ways for us together to build flashcards, per se, for the exam, inspire me to create questions for the exam, and help you fill in any gaps in your understanding. I have to admit that I went through the questions quickly first. I moved all the programming-related questions outside of this list because they're not really relevant for the study. A couple of programming questions were relevant, so I kept them. The specific programming questions like, how do I create a loop, that doesn't apply to what you didn't understand about errors or about the Taylor series or about linear solvers, for example. So that's a programming specific question. So it's out of scope, but feel free to follow up with me or Ariana or Ainsley in the office. We can spend more time with you and help you understand it better, okay? Some questions are similar, so you'll see as we go through the questions. Some of you didn't list any issues. They said, you know, this I understood the material, so thank you for that. So I deleted those questions. There might be a couple left. So, all right, let's get started. I still get confused sometimes when trying to remember the difference between truncation and round-off error. Here's the rule. Truncation error has to do with mathematics. Round-off error has to do with computers. Truncation error has to do with taking a long, infinite mathematical formula and chopping it to a finite size number of terms so that we can digest it and put it on a computer. Once you put it on a computer, you have round-off error. Whenever you have multiplication, addition, division, subtraction, you have round-off error, okay? So let me see. Okay, so truncation error has to do with math. Round-off error with computers. Okay. So when to use which type of error? So the question here is referring to whether we use true or approximate error. And remember, those were the two types of errors. Now, each type has a way of computing it. Either you do it in absolute form or relative form. Okay? Always go for relative, and it's rare in practice to have a true error. So a relative approximate error is your go-to type of error that you will have to use. Now, if I tell you, like in the homework problem, here's the true value, really there's no true value. We cannot know anything in truth. Even unless it's like an analytical verification case, then use the true value, okay, and use the true relative error. Okay, unless otherwise stated, okay? All right. So I don't think I have time to type them now. We'll type them up later. Maybe Ariana. Maybe I'll do I'll pull the transcript of the recording and then just copy paste. My accent is pretty good now, so YouTube can actually kind of translate me like 90% of the time, transcribe my words. Okay. Siri has problems with me all the time, though. Using absolute value of errors, is this something we should always do or only for specific cases? It's up to you. Again, as long as you can measure an error, that's a very important thing. Now, does the sign of the error matter? So I give you an example when it's important. Let's say you're measuring something in air quality. Is your pollutant increasing or decreasing? Right? So I could report an error of 2% in sensor measurements for particulate matter or some radon. But is the radon increasing or decreasing? Or is the PM increasing or decreasing given that baseline value? So in that sense, a nominal value, non-absolute value, without absolute value would be useful because it will tell you the direction of the error. Are you overestimating or underestimating? Okay? But for the most part, an absolute value of the relative error will be important. I will tell you, if there's a question, I'll tell you, measure the true relative, measure the relative true error in absolute value, for example. Okay? Good question. With relative error, since it has to be calculated based on the previous estimation, what value do we use as the relative error for the first time? Do we just ignore it and say not available? That's a great question. So the person who asked the question is thinking in terms of the Taylor series, for example, or doing successive approximations of the derivative. As we refine in the grids, in the spacing for the derivative, or as we add more terms. Well, when you start with the first term of the Taylor series, there is no previous approximation. It is the first approximation. So what do you do in that case? You say the error is not available or is 100%. Okay? So there's no, you cannot define an error in that case because there's no previous approximation, right? You only have that one approximation. Great question. One of the least clear things to me was how to address the error once we have analyzed it to see that it is there. The question remained for me whether or not errors can be compensated for in each iteration, or whether it is best to do it at the end of the calculation. All right, so error is something you have to live with. Agreed? Think of the error as a way to assess a method or technique. So for the Taylor series, we noticed that with less terms, you're going to have larger error. Clearly, to address the error in that case, you have to add more terms, right? With the derivative, you have to reduce your spacing. But then we also saw that if you keep reducing it so much, then round-off is going to dominate. There's another question about that I will address too. But there's a limit to what you can do. Then, if your concern is, okay, how can I reduce that error? How can I improve my method? You have to find a different method, okay? And finding a different method is just looking for other methods, maybe using a higher order approximation for the derivative, a second order, a fourth order, or so on, right? So that becomes a kind of a different question. But it's a good question because you look at the error and you're asking, how can I improve? So if you're working with a experimental apparatus, for example, and one method of measuring flow rate is giving you a high error versus another method, then you can compare the two, right? So the error gives you this ability to compare two approaches. Use the one that gives you less error. But maybe that error is going to be dependent on humidity, on pipe sizing, on Reynolds number, etc. So you start taking all of those into consideration. So it's the beginning of a discussion per se. All right. A discussion of how error tolerances impact different areas of chemical engineering would have been very helpful. I agree. It would have been super helpful. It seems like there is inherent error in each kind of calculation done by numerical methods, but determining what is the best error tolerance for different kinds of situations would be enlightening. That's a great question, and I wish I know the answer. The fact is, I'm not an expert in all chemical engineering aspects. I can tell you in the numerical methods for specific fluid flow problems or heat transfer problems what tolerances we're expecting. But you go to in battery design or biosensors, etc. The tolerances are going to be specific to the discipline. But that's a good thing because learning these tolerances right now is not going to help you because you're not immersed in that specific area. Now you could research like biosensors, what is an acceptable error in biosensors, for example. There are some, or what is an acceptable error in certain experiments. There are some cases where a 10% error is acceptable. To me, in my field, 10%, they would fire me, right? It's like I have to be less than a 0.1% in the methods we develop. So it depends on the field. The more immersed you are in the field, the more knowledge you will know about what is acceptable and what is not. And that is often dictated by what are the best available tools out there? And if the best available tool gives you an error of 10%, then that's the gold standard. And you accept that and move on. But it's a good question nonetheless. It would be, I think it would be useful to add a slide next year to put this in context, say, you know, in different fields, these kinds of errors are acceptable, etc. So thank you for that question. The clarity of finding the first derivative was made very clear, but I was curious if error is also part of integration and other sorts of operation that are performed on different functions. Absolutely. We will see once we do numerical integration, we have to obey the same types of errors, both from truncation and round off, okay, because all of those are based on approximations. Okay? Good insight. If I understand what these two mean in theory, I would like more practice doing more problems on error analysis. Okay, I think I trimmed off the first part of the question, which had a programming question in it. So if the question is saying, if I understand the differences between approximate error and true error, then they'd like more problems for practice, which is a good question. But you got more practice as we went to linear solvers and linear solvers, iterative solvers, and nonlinear solvers, right? So, that discussion at the beginning, we did a couple of examples in the homework for the gas station and the round-off error for the Scud missile. But then the concepts are going to be used until the end of the semester. Okay, so that's kind of your practice now, I'm hoping. The difference between true error and relative true error. Whenever you hear the word relative, there's something in the denominator. Okay, so you're measuring the error relative to something. The opposite, when you hear true error or approximate error, there's no relative to it. It's just the difference between two values. It's a nominal value, difference between two values. It is still not very clear to me how the relative approximate error works as far as how one value in the list is more accurate than the one before or after it. So you have to trust that all the numerical methods that we are using, they have been developed and created with solid theory that demonstrates that when these methods work, or in the cases where, for these most cases, except when they don't converge, But in the cases where it's appropriate to use them, then these methods they converge and they get more and more accurate the more terms you add, or the smaller the grid spacing, etc., or the more points you add. Okay, so you have to trust that. That automatically implies that with any of those approximations, for the derivative, for example, you shrink h, then the error is going to shrink. You saw the theory with the Taylor series. You saw the truncation error. It was just proportional to h, or h squared. You shrink h, that truncation error is going to go to 0. So smaller spacing, smaller h values, smaller error. So that's kind of comes from the theory. So that being said, then as you are building an iteration or a successive approximation, your current approximation, which by definition is going to be using so instead of current approximation, say more accurate approximation, whatever order you want to put them in, use the more accurate approximation. The more accurate approximation usually has a smaller grid spacing or more terms in the Taylor series, for example. Okay? So you have to trust the theory as well that the more accurate approximation is in fact more accurate. The only thing that I was not 100% sure on was truncation errors. Specifically, the value represented by xi. I just didn't understand if it was something that we could find. I think that if the person who asked the question is here, please help me understand. But I think you're referring to the bound that I put on the truncation error when I said that all of the rest of the terms, they are all less than 1/2 h f double prime of c, right? Maybe that's what you mean. And that value, you don't know that value. We could never find it. Okay, but that at least puts a bound that this is a constant, and the only thing that matters is h. not f double prime of c, because for a given problem, f double prime of c is a constant, whatever h you choose. So what matters to the truncation error is that h. As you change h, what happens to that total truncation error? If the question is referring to f of x minus xi or x0, we use x0, I think, or with the derivatives, xi. So when we did f of xi plus h minus f of xi, xi is just any point around which you are trying to evaluate a function. Call it x. We use xi because we're applying this on xi plus 1, xi plus 2, xi minus 1 on a grid in the end, right? Okay. When to use true error versus absolute error. So we answered the question. The topic I am most confused about is bits and round-off errors. I'm not super sure what a bit is. Neither am I. So it ends up slightly confusing my understanding of round-off errors. Okay. So think of the bit as something in the computer, a transistor, where you have a number. How do you put it inside a computer so that it shows up in your screen? The computer somehow takes that number, does its things, and then it has a dedicated space in memory to put that number in. So it first has to convert it into a binary representation. Why binary? Because computers are based on transistors. Transistors can have only two states, either charged or uncharged, on or off. That's why we use binary. Now, computers have limitations on how many transistors you put in memory. If you want to put the binary representation of a number, you just have to fill in the bits. When you run out of bits, you just throw away everything left in that number. What you've thrown away, that's your round-off error. Okay? Simple way to think about it, whenever you put a number on a computer, that is round-off error. Forget it. There's always round-off error. Every time you multiply, add, divide, subtract, every time you put something on a computer, there is round-off error. Okay? I hope this clears things up a little bit. There is in the chapters, in the reading material I uploaded to Canvas, there's a whole 50-page discussion on bits. And I'd be happy to spend the time on that. That will be the entire course, but I think it will not help you one bit in your career. So just understand that bits have limitations. You put a number on them. Whatever cannot fit gets thrown away. That's round-off error. I was also confused about when I present an error as a percentage or just a number. Relative errors, by definition, are dimensionless, right? So you can present them as a percentage or a number. Doesn't matter. If you say your relative error is 0.1 or 10%, that's the same thing. 10% is equal to 0.1. Right? So you present it however you like. Percentages are easy to understand because people, we've been kind of brainwashed to use percentages, and they're easy for a reason. It's a nice, simple thing about them. Non-relative errors are dimensional. They have units in them, right? They have dimensions. They're the dimensions of whatever you're computing. You cannot represent them as a percentage. Okay? I hope this clarifies. Question 18. I am still confused about round-off error. Okay, so we answered this question. Answered. When are we supposed to use which error? Also answered. See, they start coming, the same questions. Tangentially related to error. How are Taylor series used in practical engineering? When you're computing derivatives or slopes on your calculator, if you were asked to draw the sine function by hand, you take a couple of first terms and you go and draw it with lines, all the way to computational fluid dynamics, the medical devices that we use, the imaging. It's all over the place. You don't see if you go to a doctor's appointment, the doctor's not going to say, let me grab my Taylor series device and, measure your arthritis. They're not going to do that. They're going to grab a device, do some imaging. That imaging is based on technology that you all are learning, okay? I don't know a specific example right now, but I know we did a lot of ultrasounds, etc., and there's a lot of Fourier series going on there. And Fourier series, you truncate them and tie them back to Taylor series. So there's a lot of that going on. Okay, don't think this is all theory. If you haven't seen it in practice, you're probably not thinking about engineering. You're probably thinking about just simple kind of handyman work, right? I'm not going to use the Taylor series to go and add a window to my shed, although, you know, the engineering types will be very calculating, right? But, you know, that doesn't apply there. Sure, whatever, you know, but that's not the point, right? Okay. Good question. Determining, defining the truncation error and approximation, and how to display them, as in, do we just leave the applicable terms as is, or should we group or simplify? I'm not sure I understand the question, but my guess is that after we, yes, leave the Taylor series as is. Don't try to simplify it or say, look, I'm going to collect those terms and factorize. Don't do any of that. The Taylor series is the Taylor series. Leave the terms as they are, because their order is important. The squared, the cubed, the power fourth, they're all important. All of those orders are important. Whatever you truncated, leave it as is. And if you want to put an exact equal sign, put that big O symbol that we've introduced. If not, put an approximate equal symbol and move on. I was still kind of unclear as to why the error increased when we graphed the error. Okay, it's a great question. That was if you don't remember, this was just at the end of the discussion on errors when we computed the derivative of this exponential function, and we derived the truncation error for the forward Euler approximation for the derivative. And that approximation was, the truncation error was 1 over 2 h f double prime of xi, right? And so we said, well, this is the truncation error. As h decreases, the truncation error should go to 0. Now, the truncation error is the difference between a true value and the approximation, right? So the true value, we knew it to a very high degree, okay? That because we could evaluate the derivative analytically. So we took that value, subtracted it from the approximation, and kept changing h. And the curve kept dropping. If you remember, the error kept going down. And then there was a value of h where after which, pop, it started going up. Like, what happened there? What happened to the truncation error? Okay. Turns out that what was missing, that what we were plotting there was the total error, which consisted of both the truncation error, which is a theoretical pure math construct. If you had an infinite precision computer that has 1 trillion gazillion bits in it and represent numbers to a perfect accuracy, then that graph would keep going down forever, because that truncation error tells us it's going to shrink as h shrinks. Unfortunately, once you put things on a computer, f of x plus h minus f of x over h, f of x plus h and f of x, those have round-off error in them. So you're going to have a round-off error divided by h, plus a truncation error. Truncation error goes to 0 as h decreases, but the round-off error is going to amplify as h decreases. And there's going to be a point where the round-off error is going to take over. Point is, we didn't think about round-off error when we were computing that error between the derivative approximation and the true value. There is truncation error, but there's also round-off error. And that specific example was built specifically that way to show you that, well, yeah, you cannot take h on a practical computer. You can't just take h to 0. Now, if I had brought a computer with 512 bits of memory or 1024 bits of memory, I could keep driving h further down, but there's going to be a point where round-off error is going to take over, and then we'll see that curve changing signs. If you're still confused about that, come to my office and I'll show you the derivation of this. I think that remembering the difference between true error, approximate error, and the relative error was a little hard to keep track of. It's just 4 of them, right? There's true and approximate, okay, and there's absolute and relative. So it's a table, 4 errors. Okay? True and approximate, absolute and relative. All right, so I don't want to spend maybe 5 more minutes on this. I'll fill in answer the rest offline. For true error, I sometimes have difficulty understanding which error is the true value and which error is the approximate value. I get that from the homework. That was a little confusing. Excuse me. But generally, in practice, you'll only be dealing with approximate error. And you will know the one that is more accurate is the one that has more terms or has a smaller value of h for the spacing. If you're designing a numerical method, then your true value is your say you're designing a method to approximate derivatives. You're going to go and test it on a few functions. Well, evaluate those few functions analytically. That's your true value. And your approximate value is the one with the numerical approximation. Why round-off truncation errors occur? We discussed that. Computing error from a Taylor series using relative error. I think we answered that. Slide about increasing error taking over also just answered. For me personally, some of the differences between some of the errors and why they are better than others were kind of confusing, and I got them wrong on the homework. I'm not sure what, but honestly, it's probably just a terminology. It is a terminology, and different people use different things because absolute error, you could think of it as an absolute. Is this an absolute value, or this is just a difference between two numbers? Well, to me, it's the latter. It's just the absolute error is just that error between two numbers. It's not relative. It doesn't have absolute value in it. That's why I say compute the true error and take the absolute value of it, right? But it's not going to be the end of the world for those things. I will be very clear in the exam. If there's a question like this, I'll be very clear in what I'm asking you, okay? The key difference between truncation, still confused, so we answered that. Defining the Taylor series, my understanding of the Taylor series and how is a bit lacking. So this will have to be to be done offline, okay? Because it could take half an hour discussion. Please stop by this. Okay. Is there a purpose for approximate error outside of determining convergence? Absolutely. Absolutely. An approximate error is your next best thing to measuring the performance of your device. Now, in actual, in more complicated situations now, what we do, what's called uncertainty quantification and, end-to-end quantification of error, model form uncertainty, etc. But they're all based on getting an estimate of the error. So the approximate error is your best bet at estimating error. If our calculators are subject to round-off error, do we know any true value? We don't. In fact, I mentioned that last time. I argued that we never know the true value, except when we have we're working with integers or you have an analytical solution, right? That's why we use the symbols like pi or e, right? Those are the true value, but we never numerically know it. We know it to a higher accuracy, to a very high accuracy. You can treat that as the truth. But if you remember, I mentioned one time during our discussion on errors, there's really no true error. They're only in a Platonic world, or maybe with integers. But truly, we only know things to a high approximation. Okay, so what we treat as the true value is a very, very high order approximation of something, and then we use that as the truth. Good question. Perfectly honest, and there was anything, though, covering more on how to correct round-off errors. So that ties up to the previous question. Need to use other methods to reduce. No. So this is not on Taylor series. This is on round-off errors. So round-off errors that's a good question. So you could reduce the amount of algebraic operations you have to do. Okay, so how many divisions, multiplications? You could rearrange your math, or just use high-bit computers. So right now, in this day and age, and probably in the next decade or so, this is going to be a futile exercise because round-off error is getting smaller and smaller and less significant. The way you could mess things up is when you are on purpose or mistakenly changing. Don't do it on purpose, like 16-bit and 64-bit. Don't mess with that. Okay. So be careful about converting from types of floats or types of numbers, 16-bit, 32-bit, and so on. Okay. You need to make sure that don't mix and match precisions in a computer. Okay, how to avoid round-off error? So that's a similar question. I'm having a difficult time differentiating between the errors, so we answered that. Answered. Truncation also answered. Okay, so this is actually a good question, and we answered it, but the person who asked it is answering themselves. I also didn't really understand the difference between the truncation error and round-off error. I believe it is the difference. I believe the difference to be that round-off errors are computer-based, exactly, due to shortening rounding the final answer, and truncation error due to shortening the Taylor series. That's a great way of thinking about it. Okay, it doesn't have to be only Taylor series. It could be any kind of infinite series, any summation that takes forever. All right, so let's switch gears. It's 2:30. Okay, so this is also a similar question. All right, so yeah, we're almost done, actually, here. That's great. All right, let's go on to linear solvers. Sorry, maybe we might not be able to take breaks today because look at the many questions we got. Okay, with linear solvers, and feel free to interrupt me and ask questions along the way. Okay, these are your flashcards. All right, iterative solvers. I had some trouble understanding the Jacobi method. I also had trouble understanding the Python section. I get it, and we kind of rushed through it this year briefly. That's why I'm not going to ask you specific details about the Jacobi method algorithm. You're not going to be asked that. The context of iterative solver questions is, how are they different from direct solvers? They don't get you the true answer, right? They just give you an approximation to the answer. What's the basic idea of iterative solvers? Start with a guess and refine it. What's the basic idea of the Jacobi? Solve equation 1 for variable 1, equation 2 for variable 2. What's the Gauss-Seidel method? Is instead of using the old values, use the most recent values. Those are like the 5 questions that I will ask you on the exam, okay? Heat transfer example. The example got confusing at some points. Well, like the grid points. So I can't answer. That's a very general question. If you want to qualify that question more specifically, what part of the heat transfer question you didn't understand, like the discretization, the matrix, the boundary conditions, the source term, etc., just stop by my office or talk to Ariana and Ainsley. We'll be happy to explain it to you. So stop by office. I don't completely get how it is organized, like what array corresponds to what diagonal row. If you could go over this, again, swing by the office. I think they're referring here to how we did it in Python, which is not specific to the theory. The Jacobi or Gauss-Seidel iterative solvers. So Jacobi, solve equation 1 for variable 1 for x1, etc. Okay, and use old values from previous iteration. Gauss-Seidel, same as Jacobi, except use most recent available values. Iterative solvers were much more difficult to understand than regular Gaussian elimination methods. I struggled to understand both the underlying theory behind how it works and the actual code behind applying it. I get it. This is a new concept. You guys are used to Gaussian elimination. We didn't cover Gaussian elimination here. All I said was that's what's used to do the inverse. I'm happy to spend more time with you in the office to go into the more math and details. Davin.
With the Jacobi and Gauss-Seidel, so when you say they use the most recent available values, that means like they both would solve equation 1 for x1, but then Gauss-Seidel would then take that x1 to then solve for x2.
Yes.
For x2.
Yeah. Yes. It will use the lower diagonal, right? Yeah. With Jacobi, no. You have x1, x2, etc. at the previous iteration. You're just using those. You're not using the most recent values. Yeah. That's why the Gauss-Seidel converges twice as fast. Okay. So again, my office. The section on Jacobi specifically was very dense. Okay. So again, similar question. I hope it eases your mind that I told you what questions you will be asked. Okay. So you're not going to be asked about the theory of Jacobi and kind of the digging into the details, just a cursory understanding. Okay, it takes a minute to absorb these methods. I get it. And the intent was not to scare you or like make you worried, and that show you there's so much more out there. Okay? Yes?
This isn't quickly on topic, but can you like quickly explain what causes a Taylor series to converge versus it not converge? Like how to know the difference?
So the Taylor series will converge, always. If there's a series that's not convergent, it could mean that the successive terms are starting to grow, whereas with the Taylor series, all successive terms are smaller and smaller. So if you think about the theory of series from mathematics, a series will converge, like one of the simplest theorems is a series if converge with like positive terms, if they are successively decreasing and they shrink to a limit, that will converge, you'll get an answer, right? Now, by definition, the Taylor series is a theorem for continuous functions, then it would converge. For discontinuous, you could use a Taylor series, but you're not guaranteed, it's wrong to use it there because they're not convergent. You could use it away from a discontinuity and so on, right? But then it wouldn't be applicable there. And then if you use it incorrectly, it will not converge. So I don't know if that was kind of clarifies things. Yeah. 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 I guess that's a better answer of doing it, of answering it. All right. If Jacobi are going to be in the exam, it's definitely the most. Yes. So they are going to be on the exam, and you know, I know you guys will rise to the occasion and be able to every year. It's the same thing, and everybody gets those questions 100% of the time. So. I hope this helps. What the source term is and when to look for or utilize it. So a source term is something, is a mathematical version of a physical process to describe that physical process. When all physical processes that we deal with in conservation laws and engineering and physics, they can be represented as differential equations. And it just so happens that something in differential equations, you're just relating rates of change of temperature, of momentum, related to spatial rate of change of something, etc. So it's just rates of change relating to each other. But there are some mechanisms where they're not described by a rate of change, yet they affect the process. They affect the heat transfer, the fluid flow. Just like the heat being transported in a rod or in any body, it's a differential equation, but spots where you are heating the thing, those cannot be represented as a differential equation. They're just a forcing term, a source term. So maybe you've heard of the forcing term in when you're studying physics. So for example, a drag force in the parachutist example is a forcing term. Whether it's reducing the speed or accelerating the speed, it doesn't obey a differential law. It's part of the differential law, but it tags along because it's like its own standalone force. So think of it this way. You're not responsible here to derive source terms or anything like that. You'll learn that in heat transfer, heat generation. But here I will give you like the equation and just ask to discretize it, for example. Okay? But I'll give you that equation, just like I did in the homework. Okay, so discussed. Successive over-relaxation, we did not cover that. So this is in the extra material and not required. So please make sure you're using the most recent slides. I mean, this used to be covered in 2000. I used to cover this in like 2018, 17, 19, I think, last time I covered it. So make sure you're using 2024 slides, please, not old slides, right? Now, if you want more about successive over-relaxation, swing by and we'll talk about it. It's just a way to speed up Gauss-Seidel. How to determine which solver is best and most cost efficient? Look at that special slide. I don't know what number it is. That showed the matrix and direct solver, iterative solver, etc. Spend like half an hour on designing that slide. So look at that slide, please. Algorithm complexity, glad you asked. I did not initially know what the proportional to symbol was and how it compared. I think it's overall. Okay, so it's just some feedback, this question. So this is the big O notation, that order N, the order notation. I get it. You know, you might not have seen it in high school, or now you're kind of seeing it in your math. So, you know, you're exposed to it here again. The big O symbol or the order symbol It's just a way in mathematics to say that a certain thing behaves similar to a certain other thing. That's all there is. It just so happens in algorithm design, when you calculate algorithmic complexity or the number of operations, you get something like n cubed over 3 plus n squared over 7 plus n plus sine n. You're like, okay, what is the complexity? What is the order for this algorithm? It turns out that this formula, if you plot it, and as you increase n, the dominant term is going to be n cubed. Not even n cubed over 3. It's going to be n cubed. So we say that entire expression is order n cubed. And what that means specifically is that at infinity, it behaves similar to how n cubed behaves, plus or minus a constant, or multiplied or divided by a constant. That it's insignificant, the constant. Okay, that's all that this big O notation means. All right? I don't understand much about iterative solvers. I would recommend you go revisit the lectures, please. And if you're still in trouble, come next week and we can have a more in-depth discussion. Okay, I guess iterative solvers because we had less practice in them again. But I clarified to you the scope through which I will ask you about iterative solvers, okay? The only thing was Jacobi, again, same question. Do most iterative solvers use a variation of Newton's method? Iterative solvers have nothing to do with Newton's method. Okay, so I don't know how you tied those two together. The only thing I said about iterative solvers and Newton's method is that they're just both iterative. Iterative methods, they use a different approach to solve a system of linear equations. Newton's method is specific for nonlinear equations. It approximates the residual with the Taylor series. And the idea of iteration is what I borrowed from iterative solvers, okay? But they're different things. In fact, when you go to large systems of equations, nonlinear equations, you apply Newton's method, you have to use a linear iterative solver inside Newton's method. So fsolve for systems of equations is using an iterative solver inside the Newton method. So you have an iteration outside and an iteration inside. But they're different concepts, okay? I'm still confused about the difference between using linalgebra solve, linalgebra.inverse to solve systems of equations. So they both accomplish the same thing. They are both a direct way. They use Gaussian elimination or a variation of it. They both accomplish the same thing. They both solve a system of equations exactly, only except for round-off error, but they solve it exactly. Linalgebra solve just gives you the answer straight. With the inverse, you get A inverse, and then you have to apply it to the right-hand side to get the answer. So there's one more step with A inverse, but their cost is about the same, okay, as you increase the number of equations in the system. So they're really the same thing, though, internally. Okay? What's the difference between Jacobi solvers and Newton's method? Again, they're not the same. Are not the same. And I explained that a second. Can we use Newton method on linear equations, and why? What do you think?
Yes, but it's not super advisable.
Okay. So first, let's ask why you can use it on a linear equation. And let's see if everybody else disagrees or not. And this is not a democracy, so there's one true answer here, right? But I'd like to at least see, like, it's not like you vote yes or no, but you know, your vote is not going to count. But I'd like to see kind of if you give it some thought. So, yeah.
Linear equations, like each point on the line is going to have the same tangent line.
It's going to have the
same tangent line, so
Uh-huh.
that
okay.
error that we're trying to find is going to be the same.
Okay. It's one way of thinking about it. So, can we use Newton's method on a linear equation? Okay. If you want, regardless of whether we want to or not, but what do you think? This is an exam question. It's 100% an exam question. Every year, it's on the exam. And probably this year, but I'm going to embellish it a little bit this year, since I'm talking to you about it. Yes?
Yes, you can, because that's
Yeah. Yeah. So Newton's method becomes exact for a linear equation because the Taylor series of a linear equation is those first two terms, right? Secondly, you can think about it this way. A linear equation is a special case of a nonlinear equation where the variable shows up linearly. So yeah, and you can solve that linear equation in one iteration. You only need one iteration with Newton's method because, like your colleague said, those first two terms in the Taylor series, they are the linear portion of the equation. If the equation is linear, then they're going to be exact. So yes, you get it. Now, why we cannot, so my guess is that who asked the question saw a previous exam somehow on Discord or whatever, like hidden channels you guys share with each other, and like it's an arms race between you and me, right? And so, so somehow they got access to the question, but it was a written exam, a handwritten exam. So why? I explained why. But now, is it advisable? Probably not, because it's all expensive, but you can do it in one iteration. So yeah. It's not going to be a big deal. Anyway, great question, though. I did not really understand the Jacobi, so we answered that. Building my own iterative solver. Like, what do you mean? Do you want to create a new iterative solver? Then come join my group. We can do a PhD together. Or are you referring to putting it in Python? Then we can talk offline about that. The difference between the different iterative solvers, we kind of just covered two, Jacobi and Gauss-Seidel. Jacobi is the most basic iterative solver, sets this simple idea that you solve equation 1 for variable 1, equation 2 for variable 2. Gauss-Seidel improves this a little bit. The rest start improving on those ideas. Then there are other higher order methods like Krylov methods called non-stationary methods. Gets really complicated, way beyond like graduate level stuff. But for what we learned in class, it's just those two differences, that Jacobi uses old values, Gauss-Seidel uses most recent values. So Jacobi uses old values of the solution. GS uses whatever, okay, most recent. Okay. I'm still having some trouble understanding the difference in use cases between indirect versus direct solvers. Okay, so please refer. What is the slide number to that special slide? Can someone, that special slide? Okay. On slide 68, where you had us write the heat transfer equation for the individual grid points along the metal rod, it was confusing that the order was switched around for each of the TI values, specifically the terms that read for point 1, etc. I didn't switch any points. All I did was I ordered them from I minus 1, I plus 1, just by sequential order. Now, I is the point in question. You're solving the equation at point I. So at point 1, I is equal 1, I minus 1 is 0, I plus 1 is 2. At point 2, you're tracking that index I. I is your point of reference. You start with point 1, point 2, point 3, and so on, and you build those equations. I reorganize them so that I can see the pattern kind of showing, and you see that tridiagonal pattern. Okay. The diagonally dominant concept was hard to grasp. I was confused if the diagonal component of the row was greater than the other entries of the same row or along the yeah. So I put the equation for the diagonal dominance, so you can look at that to double check, to do a sanity check about it. But yes, it's for a given row, the diagonal entry in absolute value needs to be greater than or equal to the sum of all the off-diagonal entries in absolute value for a given row. Okay? So that's for a given equation, in other words. Yes. Okay. I'm confused how to use the coefficient matrix on the right-hand side when I'm not coding. How can I find those things by hand, and is it possible? I'm not sure I understand the question, but yes, of course it is possible. That's the first thing you have to do. If you've come to my office in the last 2 weeks, the first thing I ask you, where's your math? You're like, what math? You're like, where's your derivation that you're programming? You can't just program out of your mind, right? I mean, sometimes we all want to do that because we want to rush to an answer, and then we get in trouble because we don't have the guiding math showing us. So yes, of course, those equations, you need to be able to put them in matrix form, and coefficient matrix, solution variable, and the right-hand side. So if you can't do that, you're going to be in trouble for the exam. So please come to the help sessions or come to me because I don't exactly know what the question is saying. Because that's kind of exactly what we did before we went coding. So we did that so we understand what we're coding. Now, if you're having trouble converting a system of equations to matrix form, you have to get up to speed on that. Because that's like way behind us now. That's a given that you know. If I give you a bunch of equations with a bunch of unknowns, you know how to put them in matrix form. Matrix, coefficient matrix, solution variable, right-hand side. Okay? Please stop by. Okay, how to use algebra solver, compare storage for the inverse method. So C activities class, deriving equations from word problems and how to determine your B matrix from word problem. My guess is that the question is saying, okay, given an equation maybe or something in words, how do you come up with the matrix? So I would need, first thing is to convert the words into math, then from math into system of equations, then on to matrix form. I'm not sure I answered the question, but if not, feel free to follow up. I already understand vector norms, especially the difference between L1, L2, and L infinity. Vector norm, good question. So vector norm measures the size of a vector. Okay? If I give you a triangle, A of sides A, B, and hypotenuse C, you say, oh, C squared is equal to A squared plus B squared because that C is really a vector composed of components A and B. So the size of vector A, comma B is A squared plus B squared under the square root. What if I give you a vector? You know, you all love space and the universe and general relativity. I give you a vector in string theory with membrane theory with like 1,000 components. What is the magnitude of that vector? It's the square root of component 1 squared plus component 2 squared plus component 3 squared and so on. It's the same thing. A vector with 3 components, the magnitude is square root of A squared plus B squared plus C squared. Okay? Now with that magnitude is a special case of what we call vector norms. That square root of the sum of the squares is called the L2 norm because it is the squares to the power 1 over 2. That's where the 2 comes from. But you can also define a 1 norm, which is the sum of all the components to the power 1, all to the power 1. So that's the L1 norm. It's a different, does it measure the vector? Yeah, it measures something about the vector. Might not call it magnitude, but it's a measure of the something related to the vector. You can define an L3, an L4, whatever norm you want. The infinity norm is, by definition, the maximum entry in a vector. Now, when you think about array, when you think about this and apply it to arrays, you treat the array as a vector where each entry corresponds to a component in an n-dimensional vector. Then you can apply the concept of the norm to those arrays. It just gives you a measure of how big the vector is. Okay? So norms give you a measure of vector sizes. Can we pivot rows and columns in Python? Yeah, but it's kind of very annoying. So yeah, but work to get it done. Is Gauss-Seidel? Yes. I'm still pretty confused about how to find the B matrix from an equation that's given to us. So the rule, when you have, so the B matrix equation, where I'm thinking a system of equations, you put all the unknowns on the left-hand side and everything you know on the right-hand side. No questions asked. Don't have any floating known value on the left-hand side. Everything goes to the right-hand side. Okay? Then you identify your unknowns. That gives you the solution vector. The coefficients of those give you the coefficient matrix. And everything on the right-hand side gives you the B matrix. Yes?
This is back to the pivoting. Do we need to know how to pivot a matrix or just when it would need to be pivoted?
Yes, when it's not diagonally. Oh, do you need to, for the exam? Yes. Yeah. Yeah, just simple rearrangement. So that slide, I think if that slide was not sufficient, email us or, just search for pivoting. It's just very simple. You just rearrange the variables, right? Okay. If I were to ask you a question about it, it would be like a 2x2 or 3x3, nothing complicated. Okay. B matrix, so unknowns on the left-hand side and everything, on the RHS. That's your B matrix, B vector specifically. Another thing that still confuses me is what the int function does. Okay, so covered that, already answered. Gauss-Seidel use updated values. That's right, perfect. That why I get yes, so yes. Okay. Do we need to be able to do Gaussian elimination or any, no, we never taught Gaussian elimination or any specific direct method. Okay, we just learned how to use them in Python. Okay, direct or indirect solvers when applying multiple processes, for example, the parachute, the difference between can someone give me the number of that slide, please? Refer to that special slide. Yeah, the diagrams, if you don't mind.
48.
Thank you. To slide 48. Thank you so much. What exactly we will be tested on? Great question. Everything we covered in class. No, what I mean by that is, yeah, I expect you to listen to me. All right? I expect you to be paying attention. If I ask you when in doubt, you need to be able to print it out. Okay? So that's what I mean, everything in class. Now, I'm not going to ask you programming questions. Absolutely not. But I will ask you conceptual programming questions, like I said in the study guide. Like, for example, if you were to design a Newton nonlinear solver, because we talked about this in class, what inputs does it need? Right? At a minimum, residual function, a derivative, an initial guess, number of iterations, right? So that's the extent of programming I will ask about. I will not ask you about how to slice an array, how to do a for loop. This is not a programming course, okay? So the extent to which I will ask about programming is this, like what would be the inputs, what would be a convergence criterion, for example. That's fair game because that's still part of the theory. Right? And everything else we covered in class together, we talked about, we discussed, okay? And in the slides. So it should be all in the slides. Like what do we mean by Pythonification, right? Okay. How? Probably not. Probably that would be like a no-point question because it's not part, I didn't find it in any textbook, so it's not part of numerical methods theory. But how each term in a differential equation will affect its solution. When I was manipulating my derived equation for the homework assignment, I struggled to find a pattern between coefficients and outputs for some terms. I'm really not sure what the question is trying to say. The differential equation is given to you, right? You're not manipulating any terms in it. You're given the discretization, okay? This is the discretization, just rearrange it. So for this homework problem, for the heat transfer problem, you were given the discretization, just apply it at each point and come up with the pattern. Okay, so you're not, this is not a different course on differential equations. We will learn more about differential equations at the end, but again, you're not going to be asked for that. Now, if you're curious and you want to know more, again, I'm happy to chat with you and kind of dig deeper into the details, but yeah, don't worry about this. How to use NumPy to solve a problem where the unknown is in the B. Yeah, there's no unknown in the B matrix. You move your unknown to the left-hand side, you move your known value to the right-hand side. If you put an unknown in the B matrix, you're not understanding how systems of equations work or this AX equal B. There's no unknowns on the right-hand side, okay? No unknowns on the right-hand side. How to build larger systems of equations. Well, we covered this. We covered an example of this for the heat transfer problem. Luckily, big systems of equations in the thousands, They have a recipe. You can program that recipe to build the coefficient matrix very quickly. But for like larger systems with tanks, etc., like, let's say you have 100 lakes. Well, it's just 100 equations. Type them up, okay, and just, takes you 15 minutes and you're done, right? But for things that are, obviously, if there's a situation where you have 1,000 equations and there's no recipe, then you have to type it up or run it through an AI machinery to come up with the equation at each node. Gaussian elimination, I don't remember what exactly we used it for and why we would choose to use it. We didn't cover Gaussian elimination. All we said was Gaussian elimination is a direct method, and GE is a direct solver and is the standard for solving small systems of equations. Okay. How do we choose? Again, refer to slide 48. Thank you. Refer to slide 48. Okay, so I'll cut it here for large systems. Okay, so now this is more of a confirmation. Okay, great. We covered all linear solvers. We're almost there. About 20 minutes. Let's see if we can cover this. So some questions, I moved some questions from the linear solvers feedback because they had to do with nonlinear solvers. I moved them to the nonlinear solvers, just as an FYI. I'm curious to learn more about finding roots. Is the end result finding where functions cross each other or finding the zeros of each individual function? It is both. For systems of nonlinear equations, it is when you write it in residual form, it is when the functions touch each other and are equal to 0. Yeah, is that 48? 52. Oh, did I add more slides, I think, to it? Okay. Maybe you have an older version, so make sure you grab.
Is it the big graphic, the red one?
Yeah, yeah.
For me, it's 48.
Yeah. This or the one? 52. Oh, no, that's the complexity. Okay. Okay. We'll fix that. Thank you. All right. Yes. Okay. I was unclear about the math behind the solver, specifically using Newton's method, how to show it graphically. Admittedly, I was not paying attention. Okay. You're up to speed. Okay, for the Python script given for us for nonlinear systems of equations, can we put as many residual? Yes. Okay, so but make sure that your input argument is an array, and you provide an array of initial guesses. See our activity on systems of equations, nonlinear equations. I will upload that. I'll finish working on that tonight. Okay, fsolve for systems of equations. Yeah, I don't know specifically what didn't work for you, so either review slides, recording, which I will post by tonight, plus stop by. Okay, I don't get why the code. What the code, again, same thing, same as before, same as previous. It's not clear to me as I would like about what the fsolve is doing. Fsolve is Newton's method. That's what it's doing behind the scenes. Okay? And when we solved that pipe problem, we got the same answer. Every digit was the same. It is Newton's method. It's just pre-packaged nicely. If fsolve, residual, initial guess, you're done, right? That's it. So it is Newton's method. Now, why the answer changes with each guess? It doesn't change with each guess. If it's converging to the root, it's going to give you that same root. You might have some round off, error within the tolerance, but if you specify a tolerance, your root, and it converges, your root will always be within that tolerance, okay? The error will be within that tolerance. Excuse me, if you change the guess and you're closer to a different root, then you're going to converge to that other root, okay? Newton's method, what specifically about Newton's method? What specifically about Newton's That was not clear. Stop by. Okay, the method mostly makes sense. We're still trying to understand the use. Use it to solve nonlinear equations. Okay, like I'm explaining to my son the other day how planetary motions work. So we had to use FSOL. No. He was looking at me and he's like, go away. I think I need a better understanding of tolerance. Yeah, so in the context of nonlinear equations, think of tolerance. Okay, does anyone play guitar here? Like electric guitar? Okay, you've seen those Fender guitars. They have like the neck. They bolt them on the body, right? So they, in fact, like I'm dealing with this right now. I just bought one. And this is beautiful, gorgeous Lake Placid blue Fender. It was a good deal. But then I got it, and I'm like, there's 2 cracks on the neck. Okay? And I start digging, and apparently, I'll tie this to tolerance, I promise, in an hour, but just bear with me. So apparently, when they bolt the neck on the body, it's really, 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 really tight in there. And any expansion in the wood or shrinking is going to affect the body, especially at the neck, because that's where the wood is the thinnest and then starts expanding, starts kind of getting bigger surface area. That's because modern manufacturing has very small tolerances. The distance between, so the size of the neck is machined so precisely well that it fits perfectly in the hole, right, in that crevice for the body. 50 years ago, you used to have like almost 2 millimeters difference between the body of the guitar and the neck, or like 1 millimeter. That's your tolerance, okay? That's a tolerance. Now, think of it as how much do you tolerate, comes from tolerate, right? So how much would your nonlinear solver tolerate an error? That's all there is to it. Are you willing to live or tolerate an error of 1%, of 10%, of 0.5%? How do you choose that number? It's up to you. It's up to the problem. Again, take measuring the surface temperature of the sun. It's 10,000 kelvins. You can emit an error of 100 degrees. That's insignificant compared to 10,000, right? But if you're measuring, again, the table that's only a meter long or like 75 centimeters, and you commit an error of 10 centimeters, that's a big deal, right? So that's your error. That's your how much of an error are you willing to tolerate? Okay. Depends on the problem. Bisection method, we did not cover it. Okay, it is in the additional material. Please make sure you use the most recent slides. Make sure you use the most recent slides. Really, nobody plays guitar? A little bit. Okay, or like some other instrument? Okay, what?
I play trombone.
Trombone, yeah. That's nice. We did the study for the orchestra, and the trombone was one of the key instruments we looked at with the emissions, you know, through the reed, and anyway, so, well, not the reed for the trombone, but like but you know, all the respiratory droplets, etc. So, did you ever play with a bell during COVID?
Yeah, a little bit.
Yeah. Okay, the difference between the different nonlinear solvers, there was just one nonlinear solver we covered, which is Newton's method. I think the question is referring to bracketing versus open domain methods. So I will refer you back to the slides, please. In a nutshell, bracketing methods, you need 2 guesses per root in 1D, and you just home into on the root. To the root, you're always guaranteed to converge if you pick your brackets correctly. In open domain methods, you just pick 1 point, and you're not guaranteed to converge, but they're much faster. So I think that's the question. I believe we may have talked about this in the lecture. I was wondering why we are allowed to truncate the residual function of the Taylor series. So it only includes the first 2 terms. Are the other terms not significant, and could including those terms make your solution better? Beautiful question. Okay. I mentioned this very quickly during the lecture, and so I'm glad you asked this question now. So the person is asking, when we went on to find an answer for the root for r of x equals 0. R of x, that was cosine x squared e to the log x, e to the log squared x, something complicated, right? And then we said, let's write that as a Taylor series. And we only took the first two terms, and I said, we only take the linear terms. Why? Because you can very easily find one solution, one unique solution for the linear terms. And then we iterated over that. Now the question is, why not take more terms? Like, why not take the next term? We could, but that will be an x squared term. So you have a quadratic, and then you're going to have two roots. You can solve it analytically. You can build an iteration on that. But which root do you pick? You're going to have two roots. Then you go to a cubic. Then you need an iterative solver for the cubic, right? So, it defeats the point. You want a method that is very simple, right? That's why we chose only the linear portion of the Taylor series, because we can solve it exactly, only the linear portion, and get only one unique root, one unique answer. And that was the foundation of the nonlinear, of Newton's iterative method. Good question, though. Okay. I'm confused about when it would be beneficial to use fsolve over Newton's method. It won't. Fsolve is Newton's method. How do we know that our tolerance is small enough when solving? It is up to you and the problem you are solving and how much error you are willing to tolerate. I know this seems esoteric and like out of the blue, but that's the best I cannot tell you, go out into the world and use a tolerance of 1%. That's nonsense. That's meaningless, right? I can't have that on me, right? So it's going to depend on the problem you're dealing with. How to solve a system of nonlinear equations. Refer to the activities and slides, please. Okay. When to use finite difference approximation versus just analytically? Great question. Analytical derivatives are clearly always preferable if you can derive them and make sure that they are properly implemented in the code. Okay. Otherwise, they are more likely to cause programming errors, right? So you miss a parentheses, etc. It's a common theme I've seen. Missing parentheses, so you're prone to error. So I always prefer using a finite difference. Finite difference for the derivatives. Okay, I know how to solve systems of nonlinear equations, but the process the computer is doing doesn't make sense to me. Don't worry about it. Look at the additional material to see to understand what Python is doing behind the scenes. It's understandable. It's very complicated, but I think you can understand it if you spend time on it. In fact, I used to teach it as a requirement in this course. You get these Jacobians and their inverses, and you have to use iterative solvers on them. It gets really complicated. I'm struggling to understand how to find initial guesses to start. Yeah, I know. I struggle too with I struggle with initial guesses as well. Best thing you could do is to try to plot the residual and visually identify where a root is located. Otherwise, the guess will almost always be inspired from knowledge about the problem. So, if I were to do the nonlinear heat transfer problem, for example, with radiation, I showed the equations just briefly in the slides. What initial guess I would use there? I would use the average temperature. So one end was 300, the other was 500, put 400. Always converges. That makes sense. It's like, okay, it should be somewhere in that range between 300 and 500. There's no reason for it not to, right? So you'll most likely have additional information about a problem, or you have to seek out additional information about it if you cannot plot it. My main problem was, excuse me, with translating the known equation into a formula that a computer would understand. This most game doesn't understand exactly how to figure out which variables should end up on which side of the equation when it got converted into a table. Okay, I think this belongs to linear solvers, and the table refers to the matrix. That's my guess. I'm going to move it here. Okay. Put all unknowns on the left-hand side, and the known values on the RHS. Okay. All right. I wasn't entirely clear when using more I'm using more accurate approximation versus less accurate but less intensive method. I think this relates to the different derivatives, right? The different derivatives we use for the residual derivative. Remember, there was a slide where I had the forward Euler, the backward Euler, and the central method. One of them was order H squared. We said one of them requires more function evaluations. I think it was one of you guys who answered the function evaluations question. So I think that's what the question is referring to. If I can be an oracle. Yes, so I think this question relates to the finite difference derivatives for the residual function. We had a couple of methods. One of them was lower order, first order, but it was fx plus h minus f of x, but we're already evaluating f of x, so we're only doing one more function evaluation. So we could reuse f of x in that calculation. Whereas the other method was f of x plus h minus f of x minus h. So you have two more function evaluations. Now, for a single equation, this is meaningless. Even for 100, this is meaningless. But when you're doing this for 1,000 equations and repeating it over and over and over and over again because you're solving a transient problem of fluid flow or a fire spreading, it becomes a big deal. One additional function evaluation could cost you hours, if not days. Okay? So that's I think what the question is about, and that's kind of the answer. I hope this helps. Do we have to have root guesses from a visual? Yes, for most cases. In general, you will have intuition about your problem to choose a guess. Conceptually, I don't really understand step 3 and 4 in Newton's algorithm. Check for convergence. If not converged, set x0 equal x1. So what we're saying here, you find an improved guess for the root. Okay, that's your x1. Check if it's converged. If it's converged, then quit the loop. You're done. If it's not converged, reuse that new x1, that new guess, as your new guess. So set x0 equal x1. So now use the new x1 as your guess and start over. Yes?
So,
Sarah.
we have like open domain versus closed domain. We pretty much only did open domain because we just gave a guess, not a label.
Correct. That's, yep, spot on. Yeah, we did not cover closed domain methods. Only we said they exist, and that's it. If you want to learn more, there's a lot discussion at the end. In previous years, 2018, 2019, if you find the playlists, they're on Canvas. I dig into more depth into those, okay? All right, so I think I'm done. 2 more minutes. Conceptually, okay, using fsolve, importance of initial guess, we answered that. The thing that was unclear, how with systems of, again, refer to slides, activities. Okay. 24, I also currently confused about how numerical derivatives work. I'll figure this out after doing the homework, right? I was most confused on the effect of the local minimum maximum and approximately how far from 1 it should be. And you need to be outside the minimum because that if that initial slope gets you into the minimum, you're going to be stuck. So you need to be outside the local minimum. If the slope is going down, if the curve is going down, get out of that minimum, away from it. If it doesn't, you go to another side. Go to the other side of the root, okay? You need to stay away from local minima. Okay, so I'll continue answering those offline. I think one of the least clear things to avoid getting caught. So the same answered. Answered. It was not clear exactly what sort of values made up the composition. Okay, so this question about the residual vector, I think that refers to linear solvers. So I'll answer that. All right, everyone. Thank you. I'll continue working on those, and I'll post them hopefully between now and the weekend, Friday. Okay? Thank you so much.